Imagine you're managing like a massive GPU cluster for a frontier AI lab and you've got this fixed compute budget. Welcome to AI Paperslop, the YouTube series for AI researchers and ML engineers, where we summarize the latest AI and tech papers. Today we are jumping straight into a newly released paper called Understanding Reasoning, from Pre-Training to Post-Training by Jingyin Shen, and a joint team from NYU, Modal Labs, UCLA, UIUC, and Columbia. And here is the TLDR right up front.
Yeah, no standard intros today. We are getting right into the core insights.
Exactly. So this paper basically establishes a joint scaling law that connects your pre-training choices directly to your reinforcement learning post-training. The main takeaway is that your pre-training loss strictly predicts your ultimate post-RL performance ceiling, so your pass at one metric. While the amount of pre-training data, your token count, that dictates the slope. It literally tells you how fast the model is going to improve during RL.
Which is just a massive finding for the field.
Right. Furthermore, the authors prove that RL doesn't just, sharpen a model's existing preferences. On hard problems, RL actually surfaces buried knowledge, which they call tail discovery, while simultaneously reinforcing confident mistakes, which is wrong mode amplification.
And to validate why this is such a massive deal for everyone listening, you have to realize that systematic sweeps across pre-training and RL are usually prohibitively expensive in LLMs.
Oh yeah, like bankrupting your entire GPU cluster expensive.
Exactly. So to prove this scaling law definitively, the authors had to build this really brilliant, fully controlled testbed.
Which makes sense, because studying RL in standard LLMs is just too hard, The pre-training corpora are uncontrolled, they're scraped from the whole internet, and the action spaces are massive.
Right, usually around 100,000 tokens or more.
Yeah. So their solution was chess. It has this highly compact, explicit 81 token action space, and move quality is exactly verifiable via game outcomes or engines like Stockfish.
And their setup perfectly mirrors standard LLM training, which is the genius part. They took autoregressive, dense Qwen3 decoders, scaling from 5 million up to 1 billion parameters.
And they pre-trained them on a 54 billion token corpus of lichess human games, right?
Yeah, exactly. Then they do SFT, supervised fine-tuning, and finally apply RL using GRPO on verifiable puzzles.
It's like trying to study ocean currents in a bathtub instead of the Pacific Ocean. By using chess, you can actually control the variables, run 36 different pre-training RL combinations, and clearly attribute behaviors without spending $1 billion.
If we connect this to the bigger picture, the goal here is not to build the world's best chess bot. We've had those for years. The goal is to isolate how pre-training scale interacts with verifiable RL.
Okay, but before we get to the RL part, they needed a baseline policy, right? The SFT phase. Wait, so the model is thinking entirely in raw chess notations. How does it evaluate multiple paths without English reasoning?
Well, that is where they got really creative. They generated synthetic reasoning traces, essentially chain of thought, using a smaller 200 million parameter proposal model.
Oh, wow.
And you're right, it's not English. It is a depth-first serialization of a prefix tree of possible chess moves.
So they essentially built a structural map of the immediate future game states.
Exactly. They generate multiple plausible continuations from a root state, merge them into a tree, and then convert that branching path into a flat sequence of tokens. They put this specific sequence between a T tag and an NT tag.
Okay, I see.
So the model is simply predicting sequences of plausible game continuations that share a root state, mimicking search behavior entirely in token space.
And that is a crucial distinction, because when they did SFT without those reasoning traces, it only improved pass at 1. The pass at 8 and pass at 16 metrics stayed completely flat.
Meaning the model lacked any internal diversity in its generations.
Right. But SFT with the reasoning traces improved all the pass at K metrics, giving the model that necessary diversity.
Which you absolutely need if you're going to apply RL later.
Yeah. And that brings us to the actual scaling law. Once they had the baseline, they mapped out isoflop curves across 11 compute budgets, going up to 52 billion tokens.
And this is where that joint scaling law emerges. They found that the post-RL downstream performance, your pass at 1, is tightly predicted by the pre-training loss.
So pre-training loss basically equals your ceiling.
Exactly. And the slope of the RL reward curve, meaning how fast performance improves per decade of RL compute, grows approximately linearly with the log of pre-training tokens.
So model size gives you a slight boost, but the raw data exposure, the tokens, is the primary driver.
Right.
Okay, let's unpack this. If I'm an engineer with a fixed compute budget, what does this actually tell me about where to spend my FLOPs?
Well, they combined their joint RL law with the chinchilla-style pre-training loss law to trace out a compute optimal frontier. And they found that RL is highly initialization limited.
Meaning, if your pre-training is weak, you're just out of luck.
Pretty much. Spending a ton of compute on RL yields very limited gains if the prior is weak. However, as the total compute budget grows, the optimal allocation actually shifts toward RL.
Like, by how much?
The compute optimal RL share increases from about 20% at the 50 million parameter scale up to 28% at the 680 million parameter scale.
Oh, interesting. So the bigger your operation, the more you lean into RL.
This raises an important question, though, regarding the whole era of experience debate going on right now. A lot of people think we can just shift budgets to RL self-play. But this shows that while RL scaling is real, you absolutely must pay the pre-training toll first.
Yeah, there are no shortcuts. But okay, what is the RL actually doing to the policy? Does it just sharpen what the model already knows, or does it discover new things?
That's the big debate, right? And the paper proves RL is not just uniform temperature scaling. Its effect actually changes based on difficulty.
Yeah, I found this part fascinating. On easy puzzles like bins 1 and 2, RL mostly does ground truth amplification, right? It just amplifies the correct moves the SFT policy already preferred.
Exactly, just making it more confident in what it knows.
But on hard puzzles, in bin 5, RL does what they call tail discovery. It surfaces correct moves that had less than a 5% probability under SFT, but it also does wrong mode amplification, where it heavily reinforces confident incorrect moves.
Right.
It's like a student cramming for a test, right? They get faster at the easy stuff, they occasionally unearth a brilliant buried memory, but they also get way too confident in their worst mistakes.
That is the perfect way to look at it. And this mixed redistribution perfectly explains why RL drastically improves pass at 1, but yields super limited gains on pass at 16.
Because pass at 16 requires broad diversity, and if the model is 99% confident in a wrong answer, it's just going to repeat it 16 times.
Exactly. And the trace structural analysis backed this up. RL improved candidate generation and search breadth, but the model still really struggled to recover deep continuations that require more than 5 moves.
So it's getting wider, but not deeper.
Yeah, exactly.
Which brings up the obvious question. Chess is an amazing sandbox, but does any of this transfer to the messiness of natural language?
Which is exactly what the authors tested next. They ran a qualitative case study on a 1 billion parameter OLMO2 model, pre-trained on 10 to 200 billion tokens of math domain text, using GSMA-K and the math dataset.
Right. And what did they see?
They observed the exact same predictive pattern. Longer pre-trained checkpoints reached higher post-RL performance, and the slope of the RL reward curve improved linearly with pre-training tokens.
Here's where it gets really interesting. Despite the massive differences in task format, vocabulary size, and training recipes, the fundamental interface between pre-training and RL remains identical.
Yeah, it proves that these mechanics are universal properties of autoregressive models, not just some artifact of playing chess.
Which is incredible for the ML engineers listening. But I want to leave you all with a final thought to ponder as we wrap up today's analysis. The papers show that even with RL, models struggle to expand search depth beyond 5 moves, heavily favoring breadth instead.
Right, they just can't see far enough down the tree.
Yeah. So if RL is bottlenecked by the pre-training initialization and verifiable outcomes alone aren't teaching the model to search deeper, do we need fundamentally new post-training objective functions, like ones that explicitly reward the depth and structure of the reasoning tree rather than just the final binary outcome?
That's going to be the critical hurdle for the next generation of reasoning models, for sure.
Absolutely. Well, thank you for joining us for this deep dive. Keep iterating, keep experimenting with your compute allocations based on these findings, and we will see you in the next one.